Hello everybody. We are going to start today chapter 8, and chapter 8 talks about rotational motion. We touched a little bit on rotational motion. We talked about circular motion in chapter 5. This is kind of like the same thing, but we are going to study it from another point of view. Another thing is you need to remind yourself a little bit about chapter 2. Chapter 2, remember, we learned about kinematics of motion in one dimension. So we learned about the position x, we learned about the average velocity v and the average acceleration, and from there we derived all the equations of kinematics at constant acceleration. We are going to do the same exact thing here in chapter 8, but in rotational form. So what you learned in chapter 2 will be echoed here again, but in a form of circular motion. So reminding yourself about what happened in chapter 2 would be helpful. And during this chapter, I will be also talking about chapter 2 every now and then, just to make the comparison, because that's actually we build a solid understanding of the material. Okay, so this is here rotational motion, and I'm going to draw a circle, then we're going to talk about rotational motion in a second. So this is a circle here, and we can think of it like this is a path or a trajectory for an object, and this object was here at t equals t1, and the object is moving on a circular path and was then located at another position t equals t2. Now, if we want to look at the position, I said position, but which position is that we're looking for? Let me remind you what happened in chapter 2. In chapter 2, we made this the origin, okay? And from the origin, we call that the reference. So any point you draw, I'm going to call this x1, and it's a displacement, so it's a position. And there's another position here. We also measure it with respect to the 0th, so that's x2. Okay, this is one-dimensional motion. So the object at t1 was at position x1. Then at t2, the object was located at position x2. And from there, we derived, we said, for example, this area here, or this segment here, we called it the displacement, such that the displacement is equal to x2 minus x1, if you remember that. And we also mentioned something about velocity. We said velocity, or average velocity, is going to be equal to x2 minus x1 divided by t2 minus t1, and so forth. And we continued working on this until we actually worked on the whole chapter using just this segment of line. Now we are going to do the same, but we are going to use the circular motion. Look, the object was at this position, but what position? Okay, I think we should try to define the position, what position that is. The object was at this position, an angular position. If you look here, this is kind of like, I'm going to call it an angular position. I'm going to call it angular position number 1, theta 1. Okay, and the object was at angular position number 2 here. So we measure the position with respect to what? The positive x-axis. So this is the positive x-axis. So that's what we do always. We measure the position, we call it angular position. So if I may measure this position of the object with this way from the positive x-axis, look, just like we started here from the position, the origin, we measured everything with respect to it. This is our reference level. This is our reference level. Okay, so I'm gonna call this theta 2. Which one do you think is bigger, theta 2 or theta 1? Okay, of course theta 2 is bigger. As I did here, found the displacement, I can find something else here. I can find what I would call the angular displacement. So if I take theta 2 minus theta 1, okay, so this here is theta 2 minus theta 1, that will give us something we know as the angular displacement, or delta theta. Okay, so let's define things as they should be. Okay, so theta 1 is, and theta 2 is angular position for the object at t equals t2. So it's the same thing, angular position, but for t equals t2 after some time has elapsed. Now delta theta is actually what we call the angular displacement, same as when we talked about just the linear displacement, angular displacement, which is basically theta 2 minus theta 1 as noticed above. Something very important you must know, those angles are floating. What I mean by that, they are not preceded by cosine or sine or tan or any of those trigonometric functions. If you see theta floating on its own, you cannot measure it with degrees. That would be that would be basically incorrect. Okay, so when you measure theta 2 or theta 1, these are angular positions. All these angles, theta 1 and theta 2, are in radians. And I don't know if you heard about radians before or not, but it's an indication of how you measure the angle. Degrees is an indication, radians is an indication. Radians and degrees actually are not kind of like units, they are just kind of an indication, as I mentioned, so they are not units. But so for example, you've heard for if the angle is 180 degrees, okay, in rad is pi rad, okay, and you know pi is equal to 3.18 as a number. Okay, so 180 degrees is 3.18. Okay, so as a quick example, what is 45 degrees in radians or rad? Okay, well, there's a way you can do that. So you can just say 45 degrees multiplied by 3.14 and divided by 180, because 3.4 and 180, like, you're basically equal to 1, because this is in rad and this is in degrees. But 45 degrees in rad is equal to 0.785 rad. Let's have another example on changing or converting an angle indication from radians to degrees. Okay, so in this example, let's say find what's 1 rad in degrees. So what is 1 rad in degrees? Okay, well, how do we solve this one? We know that 3.14 rad is equal to 180 degrees. We need what? 1 rad is equal to x. We don't know. So x is equal to, usually you can use this as always like kind of relationship build. So x is equal to this times this and divided by this one. Okay, so 1 rad times 180 degrees divided by 3.14 rad. Now remember, rad with rad, even if it's an indication but it goes away, 180 degrees divided by 3.14, is going to be equal to 57.3 degrees. So you can rest assured that 1 rad is equal to 57.3 degrees. I would memorize this number if I could, because it's going to give us like a direct relationship, and a direct relationship is just a simple thing you can use in an equation or in a homework or even an exam, and it gives you the answer really quickly. So 1 rad is equal to 57.3 degrees. All right, let's look at this circle again here, and if I want to look at this part of the circle, this is called the arc, and the arc is actually confined by 2 things that are connected from the center, and these 2 things are known to be the radius. So this is r and this is r, and here is the angle. I'm gonna call it theta or delta theta, but let's just call it theta. This is like the angular displacement. This arc here, I'm gonna call it s. Now, what is the relationship? Of course, remember, theta is in radians, so this theta is in radians. Remember that. If you were given that in degrees, you should totally, first thing to do is to convert it into radians. So what is the relationship between s, r, and theta? Okay, as a matter of fact, this relationship was solved long time ago, and s is equal to r times theta. So this arc here, okay, the length of it, if you may, in meters, is equal to the radius times the angle confined by the arc. This is very, very important equation. Okay, do you guys remember what the circumference of a circle is equal to? Anybody remembers? I have a trick for you. You're gonna be amazed. You're gonna love that. Okay, are you guys ready? Okay. Alright, so you remember the circumference of a circle is equal to 2 pi times r. Remember that one? Please, I hope you remember that one. That would be good. That's the circumference of a circle is equal to 2 pi times r. How did we get that? Look, what is the angle that is confined by the arc of a circle? Do you see that? That's the arc of the circle, not this one. This is a little one. The angle here confined is basically 360 degrees, right? The whole angle of a circle is 360 degrees. What is 360 degrees in radians? Is actually 2 pi. Okay, put that here instead of the angle. Instead of s, which is the specific arc, that turns into c, and theta is 2 pi, and r comes down, and voila. Look, this is it. That's how we got actually this equation. That's how we got the circumference of a circle is equal to 2 pi r, because 2 pi is 360 degrees for the whole circle, and r is just the radius of the circle. Isn't this amazing? I mean, you gotta love these little things. Okay. As an example, we will talk about 2 cars that are going on a roundabout. Okay. Let's assume this is a roundabout. So you have a car number 1 here and a car number 2 here. Okay. And the angular separation between these 2 cars is 15 degrees. So that's called the angular separation between these 2 cars is 15 degrees. Now the question is, if the radius is given to be 30 meters, first of all, find the separation in rads. So find separation between the 2 cars in rads. Okay, so that's 15 degrees. What do you have to do quickly? What do you think? So to get that in rad, just in rad, you just divide 15 by what we got here up there, 57. This one, 57.3. divided by 57.3, because this is what? Degrees per rad. So this is degrees per rad, and this is degrees. Degrees with degrees go away, and this is the denominator of the denominator, so it goes up. So the answer must be 15 divided by 57.3 rad. And with some calculation, you get that equal to 0.262 rad. 0.262 rad. There it is. Now, the second part of the problem is asking us to find the arc separation. So find the arc separation. Find the arc separation between the two cars. Okay, that's S. S is equal to R times theta, and R is equal to 30 meters, and theta is 0.262. And if you do this calculation, you will find the arc separation between them is 7.85 meters. Perfect. Okay. All right. Now, if car number 2 is traveling, so let's say this is car number 2, this is car number 1. Now, car number 2 is traveling at 10 meters per second. Okay. How much time would it take car number 2 to complete a circle? So, how much time would it take car number 2 to complete one round? And I actually meant to write this down in front of you. I hope you were not bored following me, but when you ask about time, it takes something to complete one oscillation or one circle or one thing that repeats itself. What do you call that? So this whole thing, time it takes the car to complete one circle, this time is known as the period. That's what we call it in physics. And the period, it's not just any time. You cannot just call it t, small t anymore. No, you have to call it big T. Even some physicists call it tau, to make sure that you do not mix the two. So tau, or the period, is the time it takes the object to complete a full circle or one oscillation, like in the pendulum oscillation, going back and forth. That's actually what? That's a period. Okay, and you did that in the lab. Okay, so how do we do that one? Let's see. We need to think about this one, don't we? Because usually time, right, is equal to what? Distance traveled divided by velocity. Okay, if a circle, to complete what full circle, what is the distance traveled, do you think? It's basically the distance traveled, it's the circumference, which is equal to 2 pi times r. Okay, that's nice. And the velocity is given. There it is. Oh, I can't write this down here, because if I do, then that's not the circumference anymore. So we can say that time for one period, which is tau, is equal to 2 pi r divided by the velocity. And please also make sure you know this equation very well. 2 pi r divided by the velocity. And that's very good. Why? Because the period now we can find is equal to 2 pi times 30, which is the radius, divided by the velocity, which is 10. Now 10 with 30, what remains is 3, so 6 pi. And the period now can be calculated to be equals to 18.85 seconds. So that's the period or the time it takes the car to complete one full circle. Okay? Alright, so what else I can ask about this? I can ask about something called the frequency. That's another important physics concept that we need to learn. The frequency is actually number of times you complete a circuit, you complete a circle in 1 second. Number of times you complete a circle in 1 second. Okay? In 1 second. Well, as a matter of fact, the frequency is defined as 1 over the period. That's another very super duper important equation you need to know. The frequency is equal 1 over the period. Okay? So, how many times, if you were asked how many times the car completes a circle or the roundabout in 1 second, you just have to bring the period and divide it by 1, or 1 over the period. So the frequency is the number of times is 1 over 18.85, and as you can see, that's a very small number, which means correct, because it takes the car 18.85 seconds to complete one circle. So the frequency is much, it's not going to complete one circle in 1 second. That's obvious. So doing the calculations for this one, we find that the time is actually very small, 0.05. Okay, now you're asking me, what is the unit? That is a good question. Time, or tau, period, is measured in seconds. So this is actually 1 over second. That's the unit. Every time you have to find the number of times something happens in a second, the unit actually is 1 over second. Or you can actually write it in more elegant way. So is equal to 0.05 second minus 1. That's more elegant. Or wait a second, actually you can write it in a much, much more elegant way, because 1 over second is the unit of frequency, and you hear this every time you drive to work or school, when you used to drive to work or school before COVID-19. Okay. You hear it on the radio, right? When you hear, what's your favorite radio station? Is it like 104.5? What's that 104.5? It's actually 104.5 megahertz. Hertz. So the unit 1 over second, or the unit for the frequency, is Hertz. And Hertz is I think he's a German scientist who studied electromagnetic radiation a long time ago, maybe 200 years ago. Okay? That's Hertz. And so when they say your favorite radio is 104 or 105.4 megahertz, this means that the frequency, or the wave that is coming to your radio, repeats itself 104 million times per second. Can you imagine that? That's what it does. Okay? All right. I think that's a good place to stop. Thank you.